Hello, this is Dr. Hanaa Assil, and today we're discussing questions and answers on chemical energetics, which is in Unit 2 of the IAS Chemistry at Excel. This is the first question on this topic. He says, zinc metal reacts with copper sulfate solution, and he gives me an equation with its delta H. And he's saying, what is the temperature rise? So what we're trying to get is the delta T, or the temperature rise, when excess zinc powder is added to 50 centimeter cubed of copper sulfate solution containing this number of moles. Now, if he wants the temperature rise, I know that Q is equal to MC delta T, so he's trying to get delta T. And the Q I can get from the delta H that he gives me, because I know that delta H is Q over N. So the Q would be delta H times N. Remember that the Q does not have a sign, so I don't need to write the minus. So it is delta H times the number of moles. So this gives me the Q in kilojoules because the delta H was in kilojoules, but then I can change it to joules by multiplying by 1,000. So now I have Q, then I can get delta T because I know that Q is MC delta T. What is M? Again, I'm going to remind you that M is the mass of the solution, and we said because density of water is 1, the mass of a solution is the same as its volume. So if he says I have 50 centimeter cubed of copper sulfate, that is the mass. C is 4.18 always, or sometimes we put it as 4.2, whatever we say. And delta T is the rise in temperature that we're trying to find. So from that equation, delta T is Q over MC, and it comes out to be 2.5. So that is my answer. Okay. The next question says, when 10 centimeter cubed of nitric acid solution reacts with 20 centimeter cubed of sodium hydroxide, the temperature rises delta T. So there is a certain temperature rise for the reaction of nitric acid with sulfuric acid in this reaction. Then he says he repeated the reaction with 15 centimeter cubed of the same nitric acid and 30 centimeter cubed of the same sodium hydroxide solution. What would be its temperature rise? You have to realize that the temperature rise is a value for a certain reaction. The Q is a value for a certain reaction. So the delta T, whether I'm talking about 10 or 15 or 20 or 30, the delta T for a certain reaction is the same. So this would also be delta T. This next question says the standard enthalpy change of combustion of propane is this. So he's given me delta H. Calculate the heat energy, which is Q, given out when 80 kilogram of propane burns completely. Now, we know that Q is MC delta T, and we know that delta H is Q over N. These are the two main equations that we need to know. What do we need here? He needs Q. And he already gives me delta H, so I can get Q from delta H. But in order to get that, I need to get number of moles. Number of moles is mass over molecular mass. You should know how to calculate molecular mass. You know that carbon, the mass number of carbon is 12. I have 3 of them. So it's 3 times 12, plus I have 8 hydrogens. Each one has a mass of 1. So the total MR of propane is 44. That means that the number of moles is 80, but it needs to be in grams. The mass has to be in grams. He's giving me 80 kilograms, so I need to multiply that by 1,000. That gives me this number of moles. Now I have the number of moles, and he already gives me the delta H, and he's asking for Q. You should realize that the heat energy, the Q, is delta H times the number of moles. We already have the delta H. Again, Q does not need a sign. The sign is only for delta H, so I don't need to put minus. Now, this will be in kilojoules because my delta H up there was in kilojoules. So he wants it in joules. He says calculate the heat energy in joules. So I need to multiply that by 1,000. So this is my final Q in joules. This next question says sodium hydrogen carbonate can be decomposed to sodium carbonate, and he gives me the reaction. But he says this is at 300 degrees Celsius. So give a reason why it is not possible to measure the enthalpy change for this reaction directly. Now remember that some reactions we cannot measure its delta H directly. We cannot measure its enthalpy change directly. For several reasons. In this case, he's saying he wants the delta H at 300. He's doing a reaction at 300 degrees Celsius. It will be very difficult to measure the delta H at 300 because at 300, first of all, water is a gas, not a liquid. So it is not this equation. So if we get the delta H at 300, the water is a gas, not a liquid. And at the same time, if I'm heating this to a very high temperature, it's very difficult to measure heat energy when I am heating it at the same time. And also because there is a lot of heat loss to the environment if we're doing this at a very high temperature. So it is very difficult to measure the delta H of this reaction when it is at 300. Then the next question says, state what is meant by standard enthalpy change of formation. Remember that the easiest question you can get in this chapter is if he says what is meant by one of the enthalpy changes. So remember that we said if we're trying to define enthalpy change of formation, we say it is the enthalpy change that takes place when what? When 1 mole of a compound in its standard state is formed from its constituent elements, because we're talking about formation. And the elements are in their standard states under standard conditions. So this is the definition for an enthalpy change in general and then specifically for formation. Then we talked about Hess's law. If you have listened to the video explaining this chapter, we explained that Hess's law says that if we have a certain reactant going to a certain product in two different pathways, the delta H for each pathway will be the same. So he's saying he wants this Hess cycle for this reaction from the standard enthalpy changes of formation. Now, we said if we're trying to get enthalpy change of formation in the cycle, that means we're trying to write the elements from which all of these are made. So, what elements do we have in this equation? We have sodium, we have hydrogen, we have carbon, we have oxygen, and you have to put in mind how many atoms of each of them. So when we write this, we write that we need 2 sodiums in its standard state, and the standard state of sodium is solid. And we need how many hydrogens? We need 2 hydrogens, so that is 1 H2, and the standard state for that is a gas. We need 2 carbons, and the standard state of carbon is a solid. And we need a total of 6 atoms of oxygen. So we need 3 O2 as a gas. Please notice that when we write these kinds of Hess cycle, you have to write the elements with the balancing and with the states, the standard states, whether it is solid, liquid, or gas. Then he says, calculate the standard enthalpy change for the thermal decomposition, which is this same equation that we just talked about, using the information in the table. Now, the table gives me what? It gives the standard enthalpy change of formation for each of these. So he's saying to form 1 mole of sodium hydrogen carbonate, I will need this amount. 1 mole of sodium carbonate, it is this amount, and so on. And you are required to use this in order to get the delta H of that equation up there that we don't know its delta H. So let's see what we're going to do. First of all, we need to determine the 2 pathways that will lead from reactants to products that will have the same total enthalpy. So what are the 2 pathways that I have? If I start from the box that is down, 2 sodium plus H2 plus 2C plus 3O2. Then I go to what? I go to sodium carbonate plus CO2 plus water in two different pathways. So either I'm going to go through delta H1 and then the delta H of the reaction I'm looking for. That's one pathway. The total of that should be the same as delta H2, which is the other pathway going directly from the elements to those products. So if we write that, we should know that remember that the delta H of formation that you have is given for 1 mole. So when I'm writing delta H1, I'm trying to make 2 moles of sodium hydrogen carbonate. So that is 2 times the value he gives me. Plus the delta H that I'm trying to find out is equal to the other one. Now, what is the other one? The other one is the formation of sodium carbonate and carbon dioxide and water all together. So all of that is equal to that first one, and I can use this to solve for the delta H of the reaction I'm trying to get. Are we following this? Okay. Then the next question, the next part of the question says, use your answer to draw an enthalpy level diagram for this reaction. So the first thing that I look at, is this reaction endothermic or exothermic? Remember, the delta H here came out in a positive number. Again, I'm reminding you, delta H has to have a sign. So don't just write 91.6. It has to have plus 91.6. It's a positive number. That means this reaction is endothermic. Endothermic means the products are what? Endothermic means the reaction takes in heat. It means the products have higher energy than the reactants. So this is the kind of energy level diagram you should draw. You should put in what are the reactants, what are the products, where is the delta H of the reaction. Okay? This is another question. He says, consider this reaction, and he's giving me bond energies. Again, we said the delta H, either you get it through Q over N, and Q is MC delta T, or you get it through bond energies. So we have bond energies here, and he's telling me, deduce the bond energy for the II bond. Okay, so he gives me the overall delta H. So he says overall the delta H is -9. And he's giving me the bond energies for the HH and the bond energy for the HI. And then I'm supposed to get the bond energy for the II bond. So hydrogen bond needs 436. So that's a positive. Plus the II bond, which I don't know, which is X. Then the products, we said it is reactants minus products, so I should have a minus here. And then I'm forming how many HI bonds? Remember, I'm forming 2 HI bonds from that equation. So it has to be 2 times 298. All of this is equal to the delta H. And he's telling me that the delta H is -9. Remember, we said to get the delta H of a reaction from bond energies, it is the total bond energies for reactants minus the total bond energies for the products. That is what we call delta H. So from this, I can solve for X. Just solve for X, it comes out to be this number. I hope it's getting clearer. Okay, this is another type of question. The enthalpy change can be measured indirectly using the enthalpy changes for the following 2 reactions. So he has 2 reactions and he's giving the delta H and he's trying to find the delta H of a third reaction. So we say that an experiment was carried out to measure the enthalpy change of reaction 2. Can you see which one is reaction 2? It's the reaction of sodium hydrogen carbonate with hydrochloric acid. He's saying 100 centimeter cubed of 1.25 mole per decimeter cubed hydrochloric acid was placed in a polystyrene beaker with capacity 200 centimeter cubed. No point behind that. The initial temperature of the acid was 21.5. And then he put 8 grams of solid sodium hydrogen carbonate. A lid was placed and the mixture was stirred, and the lowest temperature of the mixture was 14.2. Calculate the energy transferred and hence the enthalpy change of this reaction and include signs. First of all, we need to get Q. So we know that Q is equal to MC delta T. The M we already know is 100. He used 100 centimeter cubed of the acid times 4.18 times the temperature difference, and he gives me 21.5 minus 14.2, and this comes out to be a certain number. Remember that the value of Q comes out in joules, and then you can divide later by 1,000 to get it in kilojoules. So now we have Q. But what is he asking about? He's asking about the enthalpy change. So we're trying to get delta H. Delta H I should know is Q over N. So the next thing I need to get is the number of moles. Now what do I have? He's saying I need this. The number of moles is what? Is the mass over the molecular mass. He has 8 grams of sodium hydrogen carbonate. So we do the MR for that. Mass over the MR comes out to be this number of moles, and then I can get the delta H. So the delta H is the Q that we have over N, which we just calculated, and we end up with a reaction. Now, why did I put a plus sign? Can you see why I put a plus sign in here? This is because he said that the temperature went down. It went from 21.5 to 14.2. So that tells me that the reaction is endothermic, and that means my delta H has to be a positive value. Then he goes on to say reaction 3 was found to be this. So he already calculated the delta H for reaction 3. And he says complete the Hess cycle by adding the appropriate arrows and use this completed cycle to calculate the delta H for reaction 1. So let us remind ourselves, what was reaction 2 and reaction 3? Reaction 2 was the one we just calculated. So that was the sodium hydrogen carbonate plus HCl. The reaction 3, he already gave it to us. Now, what are we going to do in this Hess cycle? The reaction he's trying to look for is 2 sodium hydrogen carbonate to give sodium carbonate plus water plus CO2. Now, notice that reaction 2 is sodium hydrogen carbonate reacting with HCl. Reaction 3 is sodium carbonate reacting with HCl. And that means that if I take each of these reactions to give these products, then I have 2 pathways for my reaction. So either I'm starting from sodium hydrogen carbonate, going through reaction 1, and then going to the sodium carbonate plus HCl, or I go directly from the sodium hydrogen carbonate to give the products. So we can use the delta H's for each of these steps in order to try and calculate reaction 1. Remember that if we say reaction 1 plus reaction 3, this is equal to the delta H for reaction 2. So taking that into consideration, I would say that the delta H for reaction 1 is actually the delta H for reaction 2 minus the delta H for reaction 3. Please note that the delta H for reaction 2 was the one that we calculated, but we calculated it for 1 mole of sodium hydrogen carbonate. If you look at reaction 2 up there, it has 1 mole of sodium hydrogen carbonate plus 1 mole of HCl. In the equation that we have in the Hess cycle, it is 2 moles of sodium hydrogen carbonate. So we need to multiply the delta H for reaction 2 by 2 in order to get it for 2 moles of sodium hydrogen carbonate. And my overall delta H here comes out to be a positive number, 100.4 kilojoules per mole. Okay, the next question says an energy level diagram for a reaction with an intermediate can be drawn as shown. Which arrow indicates the enthalpy change? Remember, we said, what do we mean by enthalpy change in these kinds of reactions? The enthalpy change is actually the difference in energy between reactants and products. So that is A in this case. This question says when 0.1 mole of aqueous potassium hydroxide was added to 0.1 mole of nitric acid, this amount of energy was transferred to the surroundings. What is the enthalpy change? So he gives me the Q and he's asking for the delta H. And I should know that delta H is Q over N. If we put it in kilojoules, then the answer comes out in kilojoules. He says 0.1 mole, so my number of moles is 0.1. And he's saying, how do I know that this is a minus or a plus? He's saying this is energy transferred to the surroundings. Remember, if he says this amount of energy in the question, he says this amount of energy was transferred to the surroundings. That means it was energy given out. That means the reaction is exothermic, and that means the delta H should be a minus, not a plus. Okay, this one says the equation for cracking reaction of butane is this. Use the standard enthalpy changes of combustion to calculate the enthalpy change for this reaction. So remember, if I write this reaction, I have C4H10 to give C3H6 plus CH4. We said if he gives me information about the standard enthalpy change of combustion, that means I burn C4H10, it gives something. I burn C3H6, it gives something. I burn CH4. Remember that all of these will give carbon dioxide plus water. And you need to balance according to the total number of carbons and total number of hydrogens that I need up there. So this is the kind of Hess cycle that you can put through. We want the delta H for the C4H10 to give C3H6 plus CH4, but I have the delta H's. I can get the delta H's for each of these. So remember that going with the red arrow is equal to going with the blue arrow. So that means my delta H1 plus the others for the C3H6 and the CH4, this is one pathway, and the other sign minus 2877, that is equal to the red arrows, and that means I can solve for delta H, and it comes out to be a positive sign, which is actually reasonable since this is cracking, and we said cracking means I need to heat it in order to break it up, so it must come out in a positive sign. Okay, this question says the enthalpy change of combustion of a liquid hydrocarbon pentane was determined in an experiment. A sample of pentane was burned in a spirit burner and the energy produced used to heat water. So he has mass of spirit burner and pentane at the beginning, mass of spirit burner and pentane after burning, mass of the water that we're heating, initial temperature, final temperature, and the MR of pentane. And he wants you to get the heat energy, which is the Q, and the enthalpy change, and include a sign. So let's get the Q. We know that Q is mc delta T. We have the mass of water, and we have the temperature change. So we calculate the temperature change from the difference of the temperatures that he gives me. So that gives me this number in joules. That's my Q. Then I know that delta H is Q over N. So I need to get the N. How am I going to get the N? Well, I'm going to use mass over molecular mass because he gives me a mass of, can you see up there in the table, mass of spirit burner and pentane at the beginning is 85.6. The mass of spirit burner and pentane after burning is 84.6. That means the mass that I burned is the difference between them. So that's just 1 gram, 1.0 gram actually. And he already gives me the MR, so mass over molecular mass gives me the number of moles of pentane. If I want to get delta H, we said delta H is Q over the N, and we need a sign. Remember, we said this is combustion, burning. Burning is always exothermic, so you should put a negative sign. Give one reason other than heat loss why the enthalpy change determined in this experiment differs from data booklet. Value. We always said that the delta H that we calculate in the experiment is always less than what it should be. And we said one of the reasons would be loss of heat to the environment, but he's telling me other than the heat loss. So another reason would be maybe there was incomplete combustion, so that means not all the pentane burned properly, and as such it gave less heat. Or some of the pentane was lost by evaporation, and that means that the mass of pentane that I used is not actually the correct mass. Okay, so just the reason why this experiment would be too hazardous to carry out in a school laboratory. Remember that pentane is an alkane. All alkanes are flammable, so they will be catch fire or there will be risk of explosion. Identify the type and number of bonds broken and formed during the combustion of a molecule of pentane. So you should know what is pentane. Pentane is C5H12. We are burning this and we're breaking up the bonds in the reactants and we're forming bonds in the product. So he's telling me identify the type and number of bonds that are broken and formed during the burning of this pentane. So which bonds are being broken in the reactants and which bonds are being formed in the products? You can see that, and he says identify the type and the number. So I have carbon-carbon single bonds. How many do I have? 1, 2, 3, 4. I have carbon-hydrogen bonds. I have 12 of them. I have 8 O double bond O bonds, and then the bonds that are formed are, I have 5 carbon dioxide, but each carbon dioxide has 2 CO bonds, so I have 10 C double bond O, and I have 6 water. Each water has 2 OHs, so I have 12 OHs. Now he's saying explain why the enthalpy change of combustion of pentane is exothermic. Remember that any reaction is exothermic if the energy released due to formation of bonds in the products is more than that needed to break the bonds in reactants. So always if he says why is a reaction exothermic, then that means that more energy is released due to formation of bonds than the energy needed to break the bonds in the reactants. This is a multiple choice question. Which row in the table shows the correct terms for X and Y and the enthalpy change? Okay, you have to realize that X, of course, is the reactants and Y is the products. And then we said if the products have higher energy than the reactants, then this reaction is an endothermic reaction. Okay. Here he gives me a table again of bond energies and he's saying what is delta H for this reaction. So again, we're going to put in the energy needed to break the bonds in the reactants minus the energy that is released when bonds are formed in the products, and we get the overall delta H. So what do we have? We have carbon double bond carbon, which is 612. I have one of them, plus I have 4 CH bonds, each of them needs 413, plus the BR-BR bond, which needs 193. So these are the reactants. Minus the products. What do we have in the products? We have 4 CH bonds, so that's 4 times 413. And we have a carbon-carbon bond, that's 347. Plus we have 2 CBr bonds, so that is 2 times 290. The overall is this number, so that is my answer. Then this question has 4 choices, and for each question we need to choose one of these choices, A, B, C, or D. The first one says which enthalpy or energy change is represented by this delta H for this equation. Now, what is he doing here? He's changing K solid to K gas. So what kind of delta H is that? You should realize that this is the standard enthalpy change of atomization. If we have something in a solid and then we change it into atoms in the gaseous state, that is enthalpy change of atomization. Now, which enthalpy or energy change is represented by this equation? Now, what is this equation? This equation says potassium solid plus half Cl2 to give KCl. Well, KCl, you're forming you have two things reacting to form a product, then this is standard enthalpy change of formation. Now, this next one says which enthalpy or energy change is represented by this? Well, I have half Cl-Cl bonds broken to give Cl. So this is actually what we call the breaking of the bonds, or the standard enthalpy change of atomization. So you can regard this as atomization, or it is actually the same as the bond energy. Okay, an experiment was carried out to determine the enthalpy change of combustion of a compound. 100 grams of water was heated by burning 0.144 grams of compound X. Calculate the energy transferred in this experiment. So he wants Q. Okay, we know that Q is mc delta T. What is the mass of water? Well, he gives me 100 grams and he gives me a certain temperature change. He's saying the temperature rise of the water was 14.5. So this is the value for Q. He wants it in kilojoules. Remember, what comes out of this equation is in joules. If he wants it in kilojoules, you have to divide by 1,000. Then he says calculate the number of moles of X. Well, how am I going to calculate the number of moles of X? He says I have 0.144 grams of X. So to get number of moles, I use mass over molecular mass. The mass is 0.144, and he's saying that X, remember that up there he said that X is C5H12, so you can calculate the MR for C5H12, which is actually pentane, and you get this number of moles. Now calculate the enthalpy change of combustion. So I'm trying to get delta H. Delta H is Q over N, so you divide the Q by the N. You want it in kilojoules per mole, then we're using Q in kilojoules. Remember that you need a sign. Again, I'm going to remind you that we said combustion, burning, is giving heat to the environment. So any combustion reaction is exothermic, so the delta H must be a negative number. Then he says the data book values for the enthalpy changes of combustion of 3 isomers is this. The experimental value is very different from these values. Give 2 reasons other than heat loss for this large difference. Again, when we say that our delta H is much lower than what it should be, what are the reasons for that? Well, we said again, either loss of heat to the environment, but then he's saying other than heat loss. Or we have incomplete combustion. That means when we were burning the pentane, not all of it burned, or it burned in incomplete combustion, means it will release less heat than it should. Or when we weighed it, some of the alkane was lost by evaporation, so the mass that he's given me is actually not the correct mass. Okay, this one says complete the Hess cycle and use it to calculate the enthalpy change of combustion. So I have a certain reaction, C5H12 plus O2 to give 5CO2 plus 6 water, and I'm trying to get the delta H for that. And the information that he gives me is the enthalpy change of formation of C5H12, the enthalpy change of combustion of hydrogen. That means that I'm going to put hydrogen down there and the arrow goes up. Again, enthalpy change of formation of C5H12 means I'm forming it from its elements. So I have 5 carbons and 8 oxygens. Now, if I'm saying standard enthalpy change of combustion of hydrogen, this is the same as formation of CO2. And standard enthalpy change of combustion of carbon as graphite, this is the delta H. Okay, so what we have is, we have to make pentane, it is minus 173.2. To make 5 CO2s and 6 water, that means I have 5 of the minus 393.5, which is the enthalpy change of combustion of carbon, and the enthalpy change of combustion of hydrogen, but we're forming 6 water. That means I'm starting with 6 hydrogen, so you multiply by 6. Again, where is my pathway for the Hess cycle? Well, we're starting from the box below, the elements, carbon plus oxygen plus hydrogen, and we're trying to get to carbon dioxide and water in 2 pathways. So either we follow the red arrow, so it will be the combustion of, or the formation of C5H12 plus the delta H we want. This is equal to the other side, which is the green arrow. Doing that and solving for delta H, you get this final. Okay. Then, this is another question. He says, Hess's law can be used to determine enthalpy changes which cannot be measured directly, such as thermal decomposition of calcium carbonate. So we're trying to get the delta H1, which is calcium carbonate, to give calcium oxide plus CO2. But he's saying, I'm going to use what? I'm going to use a delta H for a reaction of calcium carbonate with HCl and a delta H3 for reaction of calcium oxide with HCl. And he's saying, if I want to determine delta H1, which pathway should I use? Remember, you're trying to go from reactants to products in 2 pathways. So in this equation, how am I going to go? I'm going to go from the calcium carbonate to calcium oxide to calcium chloride. So that is delta H1 plus delta H3 is equal to delta H2. So that means that the delta H1 is the delta H2 minus the delta H3. Please follow the arrows. It will be much easier. Using bond enthalpy values, calculate the enthalpy change of this reaction. Again, we draw out these bonds. So this is what we have, C4H8 plus Br2 to give this product. And we are going to say energy for reactants minus the energy for the product. So what do we have? We have CH bonds. How many CH bonds do we have? We have 8. Plus, I have C single bond C. I have 2 of them. So that's 2 times 3, 4, 7. Plus, I have 1 C double bond C. So that's 6, 12. Plus, I have 1 BR. That's 193. So all of these are reactants. Minus the rest on the other side. So what do I have on the other side? I have the CH bonds. I have 8 of them. Plus, I have the carbon, single bond carbon. Now I have 3 of them. 3, we're looking at the bonds, not the number of elements. So we're not looking at the number of carbons. We're looking at the number of single bonds between carbons. So I have 3 single bonds between the carbons. Plus, I have a CBr bond. I have 2 of them. So doing this calculation, you get the final delta H. And he's saying, again, give one reason why the value calculated is different from the true value. Do not consider experimental error, mean bond enthalpy values, or non-standard conditions. So we said, remember, if we're doing this from bond enthalpies, remember that bond enthalpies are given for gaseous compounds. The bond energies for each type of bond is given in gaseous compounds. If we have something that is not gaseous, then the bond enthalpies are actually not applicable to them. Do we understand that? Any bond enthalpy that we're using, any bond energy that we're using is actually for the compound in its gaseous state. Bromine is not a gas. So this bond enthalpy, when we apply it to bromine, that's not actually correct. This question says the reaction profile for an exothermic catalyzed reaction is shown. Which arrow represents the activation energy for this reaction? Again, if we're looking for activation energy, we said, where do we find the activation energy? It is the difference in energy from the reactants to the top. From the reactants to the top. So that is A. Here again, we're trying to get the delta H from bond enthalpies. So let's take a look at what we have. We have one HH bond, a half O double bond O, and this gives water which has two OH bonds. So if we calculate it from the numbers that we have, then this is our answer. This is another question. It says the reaction of calcium oxide and hydrochloric acid is an exothermic reaction. In an experiment to investigate this reaction, the following procedure was carried out. He put 50 centimeter cubed of hydrochloric acid with a certain concentration, was pipetted into a polystyrene cup. The initial temperature was measured. Then he put 1.46 grams of calcium oxide powder, weighed out, added to the acid, and he writes the maximum temperature and the initial temperature. And he's saying calculate the enthalpy change for the quantities in this experiment. So we're basically trying to get Q. And you know that Q is MC delta T, the M is 50 as he wrote, and the specific heat capacity is 4.18. So all you need to do is include the temperature change. So this is 35 minus 19.5. And that comes out to be 15.5, and you get the Q. Remember, the Q comes out in joules. If he wants it in kilojoules, I can divide by 1000. Actually, here he just wants it in joules. Using your answer from A, calculate the molar enthalpy change for the reaction between calcium oxide and hydrochloric acid. So here he's telling me to get the delta H, and I know that delta H is Q over N. So I have to get the number of moles. Well, if we go back, let's just go back for a minute, and he says he used 1.46 grams of calcium oxide. So I have 1.46 grams, and I get the MR of calcium oxide. That gives me the number of moles. The delta H is Q over N. Now again, why did we put a minus sign? Because he said the temperature rise. If we go back, it is temperature rise, so that means it's exothermic. My delta H is again, he says standard molar enthalpy change for this reaction is actually something different. And he's saying suggest 3 reasons why it is different from the actual value. Again, you have to remember, if he's asking why is it that our delta H that we calculated in the lab is different, then in this case you can say calcium oxide was impure, some energy was lost to the surroundings, there was inaccurate then measurement of things like temperature or mass or density of the solution, or when we were talking about a volatile liquid, then some of the liquid evaporated, so the mass is not correct. So these are the possible reasons that we could say cause the delta H that we calculate to be different from what it should. Here he's saying using the standard enthalpy change of this, calculate the minimum mass of calcium oxide that would be needed to raise the temperature of 250 centimeter cube of hydrochloric acid by 25 degrees Celsius. Now remember, here he's giving me the delta H, and he's asking for what? He's asking for the mass. So the first thing that we need to do is get the Q. The Q is the mass of the solution times 4.18 times 25. So we have this Q. And then the number of moles is this kind of number of moles, Q over delta H. And that means from that you can get the mass of calcium oxide. Remember that the Q up there is the mass of the solution, and we use 250 centimeter cubed of solution, so that's why we use 250 in the Q. But what he's asking for is the mass of the calcium oxide. So the mass of the calcium oxide I can get from its number of moles, so it's the number of moles times MR, and that comes out to be 7.43 grams. This question says the reaction of calcium carbonate with hydrochloric acid has this delta H. This value can be used with the enthalpy change for the reaction of calcium oxide with hydrochloric acid to determine the enthalpy change for thermal decomposition of calcium carbonate. So he's trying to get the delta H for calcium carbonate going to calcium oxide plus CO2. That's what we're trying to get. Now, what is he giving me? He's giving me a delta H for calcium carbonate reacting with HCl. And he's giving me the Hess's cycle, and he's saying use this cycle to determine the standard enthalpy change for calcium carbonate going to calcium oxide. So first of all, what do we have here? If we have calcium oxide plus HCl, that means my products here are calcium chloride, water, and we have carbon dioxide in the above equation, so I need to put it down. And then I have another pathway in which we have the calcium carbonate reacting with HCl. That also will give calcium chloride plus water. And I can see that I have two pathways. One from calcium carbonate directly to the box below, or from calcium carbonate to calcium oxide plus CO2 and then to the box below. So I can use this to get the delta H. So the delta H I'm trying to get plus the minus 196.8 is equal to the other one, minus 18.8. So in this case, the delta H is the difference between them, and that comes out to be a positive number. Complete and label the enthalpy level diagram below for the series of reactions. So what do we have? What are these reactions? These are the reactions that we have. So starting from calcium carbonate, I can either go up, and we said up because the delta H we calculated is a positive number going to calcium oxide plus CO2. Or the others are negative numbers, so I need to have arrows going down, either directly from calcium carbonate to calcium chloride plus CO2, or from calcium oxide to calcium chloride plus water, and then fill in the delta H's for each one. Okay, so this is the final energy level diagram that we have. This is another question. He says, in which of the following does X represent the bond enthalpy for the OH bond? Okay, the mean bond enthalpy for one bond. He has several equations. If you look at, let's look at equation B. He has water breaking up into oxygen and H's, and that means I am breaking two OH bonds. And that means if each OH bond is an X, then I'm breaking two of them, so that is 2X. So that is the correct answer for this question. If you look at the others, you will find that he's not breaking all the bonds. He has to break all the bonds. And he has to show that when we break all the bonds, we're breaking two OH bonds. That means the delta H will be 2X. This question has a series of reactions, and he's saying, using the symbols from delta H1 to delta H7, which of these is enthalpy change of atomization of strontium? Again, let's remind ourselves, what does atomization of strontium mean? It means formation of strontium in the gaseous state from its standard state. So atomization of strontium, can you see that it is delta H2? What happened in delta H2? It changed strontium solid to strontium gas. This is what we call enthalpy change of atomization. Then he's asking for which of these is the bond enthalpy of chlorine. Remember that the bond enthalpy of chlorine means I'm going to break the bond between Cl-Cl. So which of these is energy due to breaking of the Cl-Cl bond? If you look at delta H5, can you see what happened in delta H5? The strontium 2 plus is the same. The two electrons are the same. And the only thing that changed is the Cl2 changed to 2Cl. So that is bond enthalpy of chlorine. Remember, this has to be also in the gaseous state, which it is. Enthalpy change of formation of strontium chloride. Where is strontium chloride? Formation of strontium chloride means we need to form it from its elements in their standard state. So strontium chloride is the SrCl2 solid. Now, which of these is the enthalpy change of formation? We said enthalpy change of formation is the enthalpy change when we form it from its elements in their standard state. So it's not from strontium 2 plus, for example. So it is delta H1 that represents the enthalpy change of formation of strontium chloride. Okay, again, here he's saying the standard enthalpy changes of combustion can be used to calculate the standard enthalpy change of formation of propene. Values for some standard enthalpy changes of combustion are shown. Complete the Hess cycle below to enable you to calculate the delta H of formation of C3H6 from its constituents. So we have carbon plus hydrogen to give C3H6. We want to get the delta H of that reaction. But then what do we have in that table? He gives me information about delta H of combustion. And we said, if he gives me delta H of combustion, that means if I burn carbon, it needs this kind of energy. If I burn hydrogen, and that means the arrows go down. So when I burn carbon, for example, it forms carbon dioxide plus water. If I burn hydrogen, it will form, carbon will form carbon dioxide. Hydrogen will form water. C3H6 will form carbon dioxide and water. And please notice that we need to balance to get the correct number of carbons and oxygens and hydrogens and so on. And we write them in their standard state. So the carbon dioxide has to be a gas and the water is a liquid. And then what do we have? We said if I go from the reaction on top and then going from C3H6 to the box below, that will be equal to the other arrow. So when we have all of this, the delta HF minus the minus 2058, which is the combustion of C3H6, is equal to the other side, and the other side is combustion of 3 carbons. Please do not forget that the values he gives in the table are for burning of 1 mole of carbon, but in our reaction we have 3 carbons, so we have to multiply by 3. We have 3 hydrogens, so we have to multiply the value for hydrogen by 3. Solving for delta H of our reaction will give this value. This question, he has 3 equations. He gives me the delta H of each one. And then he's saying use this to determine the value of the enthalpy change of that reaction, carbon plus half oxygen to give carbon monoxide. So how am I going to use these 3 equations to get the required delta H? Well, you need to think and take a look at what do these equations indicate. If we have carbon plus oxygen to give CO, where is carbon plus oxygen to give CO? Well, he did not give me anything except we have lead oxide plus CO to give lead plus CO2. That's one. And then he gave me lead plus half oxygen to give lead oxide. Lead plus oxygen to give lead oxide. So that is going from lead to lead oxide. And I have one from lead oxide plus CO to give lead plus CO2. I have that. And I have one for carbon plus oxygen to give CO2. Where is carbon plus oxygen to give CO2? Can you see these delta H's, how I calculated them? So I have the delta H1 is the one for carbon plus oxygen to give CO2. So that's the one going up. And then lead plus half oxygen to give lead oxide. Well, the lead goes to lead oxide. That's our delta H2. The lead oxide plus CO, that is the equation on top. So that's delta H3. Which one does he want then? He wants the carbon plus oxygen to give CO. So that is the delta H4. So the delta H4 is the one we're trying to get. And you can see the direction of the arrows. So from the direction of the arrows, delta H1 on one end and the other is on the other end. So delta H1 is equal to delta H2 plus 3 plus 4. Put in the values for each one. You can get the delta H4 by calculation. This comes out to be this number. Can you see how we turned around the equations that he gave us in order to get what we want? Okay, think about it. Okay, the next question says, which of the following enthalpy changes cannot be measured directly? Remember that we said some reactions we cannot measure directly. For example, if I say formation of methane, I'm forming methane from what? From carbon plus hydrogen, because enthalpy change of formation is forming it from its elements. So that means I need to react carbon with hydrogen in order to form methane. Carbon does not react with hydrogen. So we cannot do that in the lab. So we have to measure it in the roundabout way using Hess's law. But we can measure combustion of hydrogen. I can burn hydrogen and we can get the temperature rise, and formation of carbon dioxide. Formation of carbon dioxide would be burning of carbon, and I can burn carbon. Combustion of carbon monoxide means burning of carbon monoxide to give carbon dioxide. I can do that in the lab. But the only one we cannot do in the lab is reacting carbon with hydrogen. Carbon will not react with hydrogen to form methane, so I cannot measure it directly. Okay, the next question is a straightforward question that says, define the term enthalpy change of reaction. Again, how do we define enthalpy change of reaction? We said it is the enthalpy change that takes place when the amount of reactants shown in the equation react to give products under standard conditions, reactants and products being in their standard state. Okay. The next question says an equation for this reaction is given, and he says the following apparatus was set up, and in the experiment he put 15.22 grams of this was reacted with excess of that. The reaction absorbed heat energy from the surroundings. The temperature of 100 grams of water fell from this to that. Calculate the heat energy. So we want to get Q. We know that Q is mass of water times 4.2 times the temperature change. He already gives me that the mass of water is 100. And I can calculate the difference between 22 and 16.5 degrees Celsius, and that comes out to be in joules. If I need it in kilojoules, I divide by 1,000. Then he says calculate the number of moles of this is actually ammonium thiocyanate. So this is what did he say? He gave us 15.22 grams. So I can use that to get the number of moles and calculate the MR, and we get 0.2 moles. Then he says calculate the enthalpy change in kilojoule per mole. Again, I need delta H. So delta H is Q over N. I have this, but remember, he's asking for the enthalpy change for this reaction, but I have 2 moles of ammonium thiocyanate. So I need to multiply the number that I get by 2 in order to get the delta H for this equation. And then remember that this is in kilojoules. So, and we need a sign. He said it was something that took energy from the environment and the temperature went down. That means the reaction overall was endothermic. So I need to put a plus sign. Okay. Then he says what is meant by mean bond enthalpy. Remember that bond enthalpy is the average amount of energy needed to break 1 mole of bonds in the gaseous state. That is the definition for bond energy or bond enthalpy. Mean means average. So you have to say the average amount of energy needed to break 1 mole of bonds. It's not one bond, it's 1 mole of bonds. And they have to be in the gaseous state. Here again, we're trying to get the delta H from bond enthalpies. So again, let us look at the bonds. We have CH bonds need 413. We have 6 of them. Plus we have 1 carbon-carbon single bond, so that's 347, plus 1 carbon-carbon double bond, so that's 612, plus 4.5 O double bond O, each of them needs 498, and this is the bonds for the reactants. So the total for the reactants is this number. Then on the other side, I have C double bond O. C double bond O is 805, and I have how many? Each carbon dioxide has 2, and I have 3 of the carbon dioxide, so that means I have a total of 6 C double bond O, times I have a total of 6 OH bonds, and that gives me the value for the energy that is released in the products. Now we said reactants minus products gives me the overall delta H. Again, he's saying data booklet value is something different. Explain why the value is less. This could be because he wants 2 reasons actually, because he has 2 marks. So we can say that the water is liquid under standard conditions, while bond energies are for gaseous states. So remember, here we're talking about delta H from bond energies. So he's saying, why is it different when we calculate it from bond energies? Remember that we said bond energies are for substances in their gaseous state. Water is not a gas under standard conditions. Now, energy is taken in on changing liquid to gas, and energy is released when changing gas to liquid. So when we're changing from liquid to gas or gas to liquid, this needs energy, and this changes the overall delta H that we calculate. The next question says the standard enthalpy change for combustion of graphite is this, and diamond it's this. What is the standard enthalpy change for reaction in which you're changing carbon from graphite to diamond? Remember, we can do this. So graphite to diamond. Now he gives me the combustion of graphite to form carbon dioxide, the combustion of diamond to form carbon dioxide, and the direction of the arrow would be the delta H we need minus 395.4 is equal to the other one, and I can get the delta H, so that comes out to be a positive number. Remember, changing graphite to diamond is something that's not very easy. Okay, this question says the standard enthalpy change of neutralization when an acid reacts with an alkali is the number of kilojoules released by what? What was the definition of standard enthalpy change of neutralization? It was formation of 1 mole of water. Remember that the definition for standard enthalpy change of neutralization was the energy released when 1 mole of water is formed from reaction of acid with base. Here again, he's saying use bond enthalpy to calculate this. Please practice all of these. So these are the bond enthalpies. We have 1 O, the single bond O, and we have 2 OHs. So that's the one in the reactants minus the products. In the products, we have 2 OH bonds plus half of an O double bond O. So overall, it is this number. Again, this is also something that we have where he gives me the equation and he says I should get the delta H of that equation from the delta H of formations of each of them. So that means that this is the kind of Hess's cycle that I should put. And remember, the direction of the arrows going from the box at the bottom to carbon dioxide plus SO2, either directly or through the CS2 plus 3O2. So that means that the 110 plus the delta H I'm trying to get is equal to the ones on the other side. Again, if we say we're forming two SO2s, that means you need to multiply the delta H of formation of the SO2 by 2. We're forming two of them. So that is 2 times minus 290. Solving for delta H, that comes out to be minus 10. I hope these questions are getting a little bit easier. The reaction for which the enthalpy change is the standard enthalpy change of formation of water. So which of these is the equation for formation of water? First of all, we said if we're saying standard enthalpy change of formation of water, we should first of all be forming 1 mole of water, not 2. And then we should be forming the water from its constituents in the standard state, and we should be forming it in the standard state. So the standard state of hydrogen is gas, oxygen is gas, and water is a liquid, not a gas. So the equation should be that first. This one says propane is sold in small cylinders for use as a fuel in camping stoves. The enthalpy change of combustion of propane can be measured by experiment. A known mass of propane is burned to heat a container of water, and the temperature rise of the water is measured. So he has mass of propane that was burned, the temperature of the water at the beginning and at the end, and the mass of water. How would the mass of propane which was burned be measured? In the other questions, how did we get the mass of propane that was burnt? Remember, in the other questions, what they did was they gave us the mass of the cylinder before burning and after burning. So he's saying the propane is in a small cylinder or in a small container, whatever. So in order to know how much propane was burnt, we measured the container with the propane at the beginning before burning, and then at the end after we burnt it, the difference would be the mass that was burnt. Calculate the energy transferred using the results. Energy transferred is mass times specific heat capacity times temperature change. So we're getting Q, the mass of the water, he says was 100, 4.18. We calculate the temperature change, it comes out to be this, and we said the value comes out in joules. You can then divide by 1,000 to get it in kilojoules. Then he says calculate the enthalpy change of combustion of propane. So we want delta H. Delta H is Q over N. So I need to get N. N is the mass over the molecular mass. The mass was 0.33 over the molecular mass of propane. So that gives me the number of moles. The delta H is the Q over the N. Again, this is combustion, so the sign must be negative. Notice that here he's saying give your answer to 3 significant figures. So 3 significant figures would be 1,510, not 151 something. Okay? The results of this experiment are inaccurate due to heat loss. So just one other source of error. Again, we said if we're burning something, there will be heat loss to the environment, but there will be incomplete combustion of the fuel. And remember that if he wants a third one, the third one would be that some of the alkane or the propane evaporated, so that the mass that we're using is not the correct mass. In this question, he says complete the equations in the Hess cycle. The enthalpy change of this is the total energy required to break the bonds in propane and in oxygen. So actually the 6,490 are the bond energies of these reactants. So first of all, he needs me to balance this equation. So this is simple balancing. How many oxygens after the arrow? We have 3 CO2s and 4 H2O. That means 6 plus 4, that's 10. So I have 2 times 5 of oxygen. Now, the C3H8, when we break its bonds, what would be the state of carbon? Remember that bond energies are for the gaseous state. So here in this case, the carbon is a gas because we're talking about bond energies. And we said bond energies are in gaseous states. And then how many O's do we need? We need a total of 10 oxygen atoms. Then he says, use the data in the table to calculate the enthalpy change of Z. Now, let's just go back and see what is Z. Z is the reaction between carbon dioxide and water to give these elements. So it is the breaking up of carbon dioxide and water to give these elements. So what bonds do we have? We have zero bond O. We have 3 carbon dioxides. Each carbon dioxide has 2 of them. So I have a total of 6 of these. Plus I have 4 water. Each water has 2 OH bonds. So I have a total of 8 OH bonds. So that is the delta H for that reaction. Then he says use the cycle in 1 and your answer in 2 to calculate the enthalpy change delta Hx for the combustion of propane. So what was delta Hx? Let us see. That was the reaction for propane plus oxygen to give carbon dioxide plus water. So this is the Hess's law that we're trying to get. Now, if I want delta Hx, it will be, we can see that following the arrow, delta Hx plus Z is equal to the 6490. So delta Hx would be the 6490 minus the Z. So let us go back. So delta H would be the difference between the 6490 and the delta H that we just calculated, which is the 8542. So that comes out to be a negative. And the other question says the data book value for propane is something different. This value is more exothermic. Why is it different? Again, we're talking about bond energies. Bond energies are for gases, but water is a liquid under standard conditions. Remember, are we talking about bond energies or are we talking about a reaction in which I burned something and so on? So the explanation for each of them would be different. This question says the reaction profile for an endothermic reaction is this. Which arrow represents the activation energy for the forward? Remember, forward means I'm going from these reactants to the products, and the activation energy is the difference between in energy between the reactants and the top. So A, it would be the activation energy for the forward. Now he's saying which arrow represents the activation energy for the backward. Backward means my products are now my reactants. So backward will be the energy of activation would be from what he writes as products, which are now my reactants. So B will now be my activation energy. Which of the arrows indicates the activation energy for a catalyzed reaction? Remember, we said when we use a catalyst, the activation energy is lower. So the catalyzed reaction would be the one with the lower activation energy. So that is A. The standard enthalpy change of formation of C2H4 is this, and for ethane is this. Calculate the standard enthalpy change for this reaction. So he gives me this reaction and he gives me information about delta H of formation for each. So we have delta H for that reaction, and we have arrows going from the elements to the top. So formation of C2H4 is this, formation of C2H6 is this, and if you look at the arrows, you can see that what we're doing is we have the 52.2 plus the delta H that we want is equal to the other one, so we can solve for delta H. This question gives a reaction, carbon monoxide plus oxygen to give carbon dioxide. He gives me the bond enthalpies. Again, he wants the delta H. So we can see that we have the CO bond in carbon monoxide is 1077, plus I have half of the O double bond O, so it's 0.5 times that number. These are the reactants minus the products. In the products we have carbon dioxide, and we said the one carbon dioxide has two C double bond O bonds, so I have 2 times the number he gives me, so this is the overall delta. Enthalpy change of combustion of methanol was measured using a spirit burner to heat a known mass of water. The temperature increase of the water in the calorimeter was measured when a known mass of methanol was burnt. So he has the mass of water, and then he has the mass of spirit burner plus the contents at the beginning, and then the mass of the spirit burner plus the contents at the end, the initial temperature of water and the final temperature of water. Now, Q, we know Q is the mass of water. The mass of water is 150. So times the temperature change, which we calculate from the difference in temperatures that he gives me. So this is the value for Q that we get. Now, he wants the number of moles of methanol burnt. Let's go back to that table. It says we have the amount, the mass of spirit burner and contents at the beginning and the mass of the spirit burner and contents at the end. So the 52.24 minus the 51.6, that would be the mass over the molecular mass of methanol. So this gives me the number of moles. Now, to calculate the delta H is Q over N. So it is the Q that we calculated over the number of moles. Again, this is burning, so it is a minus. He needs it in 3 significant figures, so this would be the answer. The experimental results differs from the true value. State one factor in the experimental method other than heat loss or incomplete combustion. So he's saying I cannot say heat loss to the environment. I cannot say incomplete combustion. I need something else. So what do we have? We said that if we're measuring the mass of the alcohol evaporates. So the actual mass that he measured is not actually what gave out heat, because it's not the accurate mass. So we don't have the accurate number of moles, and therefore the delta H is not correct. The value of the enthalpy change for combustion of methanol can be calculated from the bond enthalpies. Give 2 reasons why this value differs from the value obtained in the experiment. Again, we said the other method of calculating delta H is from bond enthalpies. We said bond enthalpies are still not correct. Why would the bond enthalpies not be correct? We said, first of all, if it involves water, the bond enthalpies are for gases, while water is liquid in its standard state. Now, the bond enthalpies also are actually average values. So when he gives you a value for bond energy, the value that he's giving you is actually an average value for this kind of bond. So it may not be exact for the compound we're talking about. Please remember these explanations. Now, he says which equation represents the reaction for which the enthalpy change is the mean bond energy of the CF bond. So he's saying which of these equations would give you the bond energy of one CF bond. So of course, if we have CF4, each CF4 has 4 bonds. So if I want the bond energy for 1, it will be a quarter of that in order to get the bond energy of 1. The following is the Thermit reaction. Draw a fully labeled reaction profile diagram for the Thermit reaction. The enthalpy change for this reaction is this. It is a minus, so he's telling me that it is exothermic. That means the products will have lower energy than the reactants. So this is the kind of energy he wants it fully labeled, and that means I put in what are the reactants, Fe2O3 plus 2Al. The products are 2Fe plus Al2O3. And then where is the activation energy and where is the delta H? The activation energy is the difference in energy between the reactants and the top, and the delta H is the difference in energy between the reactants and the product. So this is the kind of energy when he's level diagram when he tells you to draw a fully labeled profile diagram. This question has sodium hydrogen carbonate breaking up to form sodium carbonate plus carbon dioxide plus water. He's using 0.01 mole of solid sodium hydrogen carbonate added to 25 centimeter cubed of dilute hydrochloric acid. He has a temperature rise of 11 degrees Celsius. Calculate the heat energy. Again, how do we get Q? Q is the mass of the solution. So the mass of the solution is 25 times the 4.18 times the change in temperature. He said there was a temperature rise of 11. So this is Q. Now to calculate the standard enthalpy change when 1 mole of sodium hydrogen carbonate. So you're looking at the sodium hydrogen carbonate. He already gives me the number of moles. So the delta H is the Q over that number of moles. This is a temperature rise. He said there is a temperature rise of 11 degrees Celsius. That means this is an exothermic reaction, and the delta H must have a negative sign. Again, he says he needs it in 3 significant figures, so make sure that you give him the answer that he wants. Then he says the standard enthalpy change for the reaction between sodium carbonate and dilute hydrochloric acid is found by a similar method to be this value. Complete the Hess energy cycle below by adding the missing arrow and entities. Use it to calculate the standard enthalpy change for decomposition of 2 moles of sodium hydrogen carbonate. So what do we have here? We need to complete this so that we have the reactants going down with an arrow down, and what we get is when we react this with HCl, it gives what? It gives sodium chloride plus carbon dioxide plus water. Make sure that you balance each of them correctly so that you have the same number of sodium and chloride and carbon dioxide and so on. And remember to put in the standard conditions. So sodium chloride is aqueous, carbon dioxide gas, water is liquid, and complete the Hess cycle by putting in the values of the delta H. Now, if he wants the delta H of that reaction, we said following the arrow, the delta H of that reaction minus that value will give the other value. And remember that the other value is for 2 moles, so you need to multiply the delta H that he gives me by 2, and solving for that we get the delta H. This question says what is the mean bond enthalpy for CH? Again, if this equation is delta H is plus Q, so the delta H for this is Q. How many CH bonds is he breaking? He's breaking 4 bonds. So actually, the enthalpy change for 1 bond would be the Q over 4. This question says I have hydrogen plus iodine to give HI, and he wants again bond energies to get the delta H. So breaking up of an HH bond is 436. Breaking of an II bond is 151, minus the products we have 2HI, and that gives me the answer. This question says the equation for combustion of butanone is this, and he gives me the delta H for that. And then he gives me the delta H of formation of the carbon dioxide and water, and what he wants is the enthalpy change of formation of butanone. So actually what we have is we have the equation that he gives me with its delta H minus 2440, and then he's talking about delta H of formation. That means we're forming them from their elements in their standard states, and the one that he wants is the formation of butanone, so it is the delta H that we don't know. Following the arrows, you should realize that delta H minus 2440 should be equal to the others. But remember again, the others have 4 CO2, so I have to multiply the delta H of formation of CO2 by 4, plus 4 water. That means I multiply that by 4 also. Solving for delta H, I get the answer. What is meant by enthalpy change of neutralization? Again, we said to define enthalpy change, it is the enthalpy change that takes place when 1 mole of water is formed by reaction of an acid with an alkali under standard conditions. So that is the enthalpy change of neutralization. Please memorize these definitions. It's the easiest question you could get. Now, the question says the enthalpy change of neutralization between hydrochloric acid and sodium hydroxide is determined by this procedure. He put 50 centimeter cubed of 2 mole per decimeter cubed hydrochloric acid into a polystyrene cup, and he recorded the temperature. And then 50 centimeter cubed of the same concentration but of sodium hydroxide solution is placed in another polystyrene cup. The two solutions are mixed. He has an initial temperature and a maximum temperature, and the question says calculate Q. So we need the mass of the solution. What was the total mass of solution? Remember, he put 50 centimeter cubed of hydrochloric acid on 50 centimeter cubed of sodium hydroxide. That means the total mass of the solution was 100. And then from the temperature change, you can get the Q, and we said that comes out in joules. Calculate the number of moles of hydrochloric acid. Now we have concentration and volume of hydrochloric acid, so that's what we use to get the number of moles. And he says calculate the enthalpy change of this reaction. It is the Q over the N, and we said this was a temperature rise, so it is exothermic, and I put a minus sign. Thank you for bearing with me. This was a long video, but it had a lot of questions about this topic. Please practice these questions. It is an important chapter in the IAS and Excel chemistry, and please continue listening to the videos. We will go on to the next chapter.